Hi, my name is Kulavartiny.
Hi, my name is Teow Joon Hau from Chemical Engineering, and I'll be presenting on the introduction of principle of chemical engineering / material and energy balance.
Hi, my name is Maizatul Akmal Binti Mahat with student ID 200000334. Today, I'm going to present for CEB 1043 Principles of Chemical Engineering for Reactive System.
Hi, I am Farah Adlina, Binti Faizal, and I am from Chemical Engineering Group 1. Today, I will be presenting about process flow, function, and mass and energy balance for non-reactive system.
Assalamualaikum warahmatullahi wabarakatuh. My name is Abdul Raziq from Majeed, and I will be explaining about my part in this project, which is Introduction to Chemical Engineering Fluid Mechanics.
Ammonia production involves three processes, which are upstream, midstream, and downstream processes. However, in this group project, we only focus on midstream process. For principles of chemical engineering part, it solely touches on the transportation of ammonia through various systems up until storage tank, where there will be both reactive and non-reactive unit columns. There are two important processes during the transportation, which are mass and energy balance. Due to ammonia will be transported in the fluid form, we can consider the flow throughout the delivering is steady, which the mass balance equation suggests that the total mass flows into the system equals to the total mass flows out of the system. Mass balance is fairly important in the process of calculating enthalpy change and the rate of heat gain or heat loss in the system, where the energy balance takes place. Finally, before performing calculation, a simple flow diagram is essential for reference and comparison purposes.
Basically, fluid mechanics is one of the topics that are related when talking about production in ammonia. Fluid mechanics is the study of forces and motion on fluids. This is because ammonia production involves a lot of movement of fluids in upstream, midstream, and downstream. When talking about fluid mechanics, there are a few terms that we need to know before we can move on. Firstly is shear stress. Shear stress is a force that acts parallel to the surface and causes the surface to deform. The second is viscosity. Viscosity is a measure of resistance of deformation. Thirdly is kinematic viscosity, which is the ratio of dynamic viscosity to its density. There are four types of fluids that we need to know. Firstly is insoluble fluids, which are most dilute solution in organic solvent or water. Next is Bingham fluid, which can flow easily under large shear stress. Pseudoplastic fluid, which its viscosity decreases under shear stress. And finally, dilated fluid, which its viscosity increases under shear stress. Next thing is surface tension, which is the property of the surface of a liquid that allows it to resist an external force, which is caused by a cohesive force of the liquid. The final thing we need to look at is the capillary rise or fall, which depends on the magnitude of cohesion and adhesion of a liquid in the containing capillary. Liquid will rise if the magnitude of cohesion is higher, while it will fall if the magnitude of adhesion is higher. That is all from me. Thank you very much.
The first unit operation is desulfurization. We use 800 degrees Celsius as the temperature. The concentration of hydrogen sulfide is reduced to less than 280 micrograms per cubic meter to avoid nickel poisoning. Zinc oxide is used as desulfurizer due to its high sulfidation equilibrium constant. The function of this unit operation is a chemical process to remove sulfur. It is to ensure that hydrogen sulfide is not hazardous to employees and customers. It is also to protect pipeline networks from oxidizing metal interiors, compromising safety and efficiency. And this is the equation for these chemical reactions. Next is primary reformer. In this unit operation, we use 870 degrees Celsius and 30 bar It is filled with nickel, containing reforming catalyst. About 70% methane converted to hydrogen and carbon dioxide. And this is the equation for this chemical reaction. Next is secondary reformer. We use 540 degrees Celsius as the temperature. Air is added to produce a final synthesis gas having a hydrogen to nitrogen mole ratio of 3:1. Processed gas is cooled to 400 degrees Celsius in a waste heat steam boiler. The function of this unit operation is a chemical process to produce a pure gas mixture of nitrogen and hydrogen in a 3:1 stoichiometric ratio from water, air, and natural gas as possible. And this is the equation for this chemical reaction. Next is a high temperature shift converter. The gas is passed through a bed of iron oxide or chromium oxide catalyst. We use 400 degrees Celsius as the temperature and it contains a copper catalyst. This is the chemical equation for these reactions. And next is low temperature shift LTS converter. We use copper oxide or zinc oxide based catalyst. The temperature is 220 degrees Celsius. The function of this unit operation is a chemical process to ensure that the highest yield of hydrogen can be obtained from the reformed hydrocarbons.
For process flow and function, for carbon dioxide removal, CO2 from the final shift gas is eliminated. Stripping and subsequent heating removes CO2 from this responding tower. The cool MEA is pumped to the absorber tower. For methanation, catalytic methanation was carried out using a nickel catalyst at 400 to 600 Celsius and 3000 kPa. The reaction is strongly exothermic and rapidly approaches equilibrium. While for ammonia synthesis, axial and radial flow reactors are the two most common flow configurations. After the flash vapor condenses in the let-down chiller, the anhydrous ammonia is removed and stored at a low temperature. As you can see, the block diagram and all the information such as assumptions, input and output value have been written to ease the calculation. To solve this mass balance part, element balance method has been chosen. By using element balance such as CO2, N2 and H2, in result we managed to get their mole fraction. Thus, we could complete all the unknowns and proceed with energy balance part. For energy balance part, the first step is labeled the block diagram that has been drawn with temperature and pressure at the input and output. Because of the temperature and pressure are in range and could not be found specifically, thus we use the value which is the highest in the research paper to ease the calculation. Next, we need to determine the specific enthalpies individually. All the values that we have calculated is put into inlet-outlet enthalpy table to make the mathematical working look much clearer. In result, we got negative value, thus it proves that carbon dioxide removal is an exothermic process. That's all for my part. Thank you.
In mass balance, I choose a primary reformer as the reactive system. So I assume that the flow rate of exhaust gas is 1000 mole per minute and the basis of 100 moles of methane with 50% of excess air. It is a complete combustion of methane and no partial combustion. This is the equation and the diagram for the solution. Next is first, I find the theoretical mole of the air and I use this formula to find the mole of air in this stream. And next, I use the below formula to find the mole of the compound in the product stream. Next is I find the mole fraction of the inlet and outlet. So this is the formula. And this is the molar mass of the compound. Next, I calculate for the mass fractions of the inlet and outlet. And next, I find the mole fractions, mass fractions, and flow rate for each compound in the inlets, like methane, air. The next step is I find the mass fraction, mole fraction, and flow rate of each compound in the outlet streams, like carbon dioxide, water, oxygen, and nitrogen. So this is the value. So for the energy balance of the reactor system, which is primary reformer, first I assume that the 100 mole per minute methane is completely burned, and the flow rate is just sufficient for the methane burning for the methane and oxygen. The temperature is 25 degrees Celsius, and the product stream at 100 degrees Celsius is discharged. So this is the chemical equation. So methane react with oxygen, produce carbon dioxide and water. Here we can see that the 1 mole of gaseous methane reacts completely with 2 mole of gaseous oxygen to form 1 mole of gaseous carbon dioxide and 2 mole of liquid water at 25 degrees Celsius and 1 atm. Then we can see the heat of reaction is negative 890.3 kilojoule per mole. So this is the diagram for this energy balance. And then the first thing is I create this table, and then according to stoichiochemistry, which is the equation, we can see that N2 is 200 mole per minute, and N3 100 mole per minute, and N4 is 200 mole per minute. So the heat of reaction, I use this formula and I got 100 mole per minute, and then the heat of reactions is negative 890.29 kilojoule per mole. So that is kind of accurate with the standard heat of reactions. And then this is the standard heat of reaction. So now I calculate the Q. So this is all the calculations, and I got Q is 11.0173 kilojoule per minute. So that is all for the energy balance of the reactive system.
So now I'm going to explain chapter 3, which is chemical engineering fluid mechanics. So the first law of thermodynamics states that the heat is a form of energy, and thermodynamics processes are therefore subject to the principle of conservation of energy. This means that the heat energy cannot be created or destroyed. Energy can cross the boundaries of closed system in the form of heat. Energy transfer across the system boundary due to a temperature difference between system and surroundings. For a closed system, the conservation of energy principle is expressed as total energy entering system minus total energy leaving system equals to the change in total energy system. The energy added to net heat transfer to closed system and energy leaving closed system are considered to be net work done by closed system by thermodynamics, which is Q net minus W net equals to the change in total energy system. Therefore, total energy of system is expressed as E equals to internal energy plus kinetic energy plus potential energy. The change in stored energy for the system is shown below. Now, conservation of energy principle for closed system is written as: if system does not move with velocity and has no change in elevation, the conservation of energy evaluation reduces to Q net minus W net equals to delta U. Therefore, if final and initial states are identical, the change in internal energy of working is 0, which makes Q net minus W net equals to 0. Q net equals to W net. Next, we are also required to suggest the storage tank dimension and holding duration and capacity. A vertical cylindrical tank is an ideal shape for the ammonia storage tank out of all other dimensions. This is because the cylindrical tank is able to store enormous amounts of ammonia and can withstand high pressure differences without distortion. Then, the holding capacity of the tank must be high in order to store a high volume of ammonia. The reason is that the ammonia stored may deplete over time, and hence the tank must hold a large capacity of ammonia before it's being refined. Lastly, the storage tank must be made of hard materials, for example steel and concrete, that are able to withstand corrosion due to the corrosive property of ammonia. Therefore, the tank is able to hold the ammonia for a longer duration.